Now I'm recording. All right. It's good that we have people on Zoom this time because sometimes I forget to like turn on my mic or something. So you guys are kind of like my warning signs of things happening. But anyways, welcome everyone to the second Hyperloop workshop for spring 2023. We are in season 4. We've been doing this for 3 semesters already. It's been quite a long time. Today we're going to be talking about circuit analysis. So things relating to circuits, electricity, power, all that jazz. It's very, very exciting. I'm a computer engineer, close enough to electrical engineering. I love power stuff. I love building circuits. Hopefully I can spread some of that love onto you guys as well. So let's go ahead and get started. But before we get started, could I just get a show of hands for people who have been to a Hyperloop workshop before? So you've been to one of our workshops. Well, we've only had one. So you've been to the last workshop. So I presume the rest of you guys have never been to one of these workshops before. All right, there's a first time for everything, and hope you guys enjoy it and keep on coming because we have 10 more to go after this. All right. So again, today we're talking about circuits. So we'll go from like the very, very beginning. This was actually designed to kind of be like a next class, a next step up from the circuit analysis workshop we did in the previous semester. But I do understand that there's a lot of people here that are new. So instead, this will be kind of like an innovation upon the previous year. I gave similar slides to last year's audience, so I'll give similar slides again, but this time hopefully with a better understanding of how things go. Because every time we run these workshops, it's different every time. So I organized these workshops into sections, and I don't know how many sections there are for today, but we'll start with basics of electricity. So exactly how does power exist? Like what is power? What are light, or what's electricity? Why are the lights above us turned on? Like how does everything we do in today's modern society work? Because face it, like if we didn't have electricity, we'd still be living in the Stone Age. Like we wouldn't be able to do anything. We wouldn't be able to like look at our phones. We wouldn't be able to like get here in our cars. We wouldn't be able to, do things that we do on a daily basis. So what is electricity actually? Well, I say energy here, but electricity is just moving charge, moving electrons. Whether it's through like a power line like this or through like a small wire like I have right here, it's just a bunch of moving charge, and we call it energy, right? It powers our stuff. It powers our blenders, it powers our microwaves, it powers our computers. It powers everything. So methods of powering objects, I think everyone can relate to this when, you can power objects by plugging into a wall, right? Or you can power objects by plugging into a computer, maybe. Or you can just, touch wires together and make sparks. You can also power objects like that, right? Methods of generating power in our world. So instead of me telling you this, what about just getting some answers for the audience? What ways can we get power from the world around us today?
Water.
We can do water, right? We can have like a dam that generates electricity based on the natural flow of water. Anything else? Solar. We can get water from solar panels. And actually, I'm using solar panels in some of my projects right now. It's very efficient, very effective. Anyone else?
Zoom says wind.
Zoom says wind. Yes, windmills. It's funny because I think I was actually considering that for one of my projects, but I think building a windmill was too out of my zone. All right. So those are great ways of generating power. And I'm not the expert on this, but if you want to learn more about generating power, you can come to our 6th workshop, I think, which Addie here is going to host. 7? I'm losing count. 7. And Addie will talk more about sustainable energy and sustainable engineering and how the world gets power around us. I think she's a very passionate person when talking about that, so I would suggest you all go to that. But in this case, we're just going to understand like how power comes to us on a daily basis. And yes, power comes to us by electrons moving through a wire, whether it's through DC means or AC means, electrons moving in both directions. But, generally, the passage of these little particles going through a wire is what powers our daily life. So why electricity? Why are you here in this workshop? Why are you learning about electricity? Why are you learning about circuits in the first place, right? It's like magic. It's like a crude comparison, but sometimes electricity does feel like magic. How many of you guys have phones that have wireless chargers where you can just like put it onto like a table and have it charge, right? I do. It's like a magic. There's a cool little science behind that using induction coils that you'll probably learn later on, but it's, magical when you can just see that, you don't see the charge, right? You can't see electrons, you see on the table. It's also used in many engineering applications, and I would like to say like all engineering applications, but some of the mechanical engineers would disagree with me. But, many engineering applications, like this car over here. This is the soccer bot that Hyperloop has built for the robotics competition. I mean, it uses power, right? There's a huge battery on the back. A lot of stuff is powered using batteries these days. Yeah, so robotics, vehicles, spacecraft, city planning, computing, all of these require electricity in some way, some form. Again, my point is we can't survive without it. I think we can all agree. So to define electricity and to go about doing this, let's get a little bit more specific. Now let's go with something that you learned in your first class in electrical engineering, right? What's current, voltage, and resistance? Let's get the three main things. Now current is pretty much the rate of change in moving charge. And if you haven't taken calculus or you don't know what this means, this is just the derivative of charge, right? Charge is a bunch of electrons, and when electrons are moving, it creates current. So the derivative, or the change in charge, is just current. And we represent current using the letter I. So I equals dq over dt. And if you ever just see like a fraction that kind of looks like that, that's known as a derivative. We're analyzing this as basically charge in respect to the change of time. The denominator is like what changes. So as charge moves through time, that's current. Higher current just means faster moving electrons, and pretty much higher current also means hotter wires. If you have more current moving fast through like a wire, you're going to get hotter wires due to friction, charges rubbing against the wires. Then, hotter wires are usually a bad thing because you don't want stuff to get hot in electronics. It's kind of like not good. But most of the time, like, things can get hot if they're even supposed to work, like motors, right? Motors draw a lot of current. Things like your microwave have a transformer in it that basically multiply your amount of power that draws a lot of current, which is why you usually can't operate like two microwaves at the same time inside a house on a breaker, or else, your breaker will explode. Not literally, but, high current is dangerous. So there's a debate in basically saying whether current or voltage hurts you. In reality, it's a little bit of both. But in this case, when we say high current is dangerous, just generally it is dangerous, no matter like what voltage you're at. If you have like 0.01 volts and it's a high current, it probably won't damage you. But in general, you want to stay away from this. It's even so dangerous, there's labels on the machines that operate really high currents, just so you don't like brush up, touch against it, and have all that current discharged through your body into the ground. Because what's going to happen is if you touch like a power line or something, all that current's going to go through your heart. And your heart doesn't like that because everything in our body is controlled by electrical signals and electrical impulses. Your brain is basically powered by electricity. Your heart is, something else in the body is. I'm not a body doctor, but yeah, neurons, yes. But pretty much all that electricity that goes through your body messes up that electrical connection, and you die. So even 1 amp is enough to kill you. By the way, this is kind of like a crude interpretation of a Tesla coil. There's not actually much current going through here. It's more of the voltage, which we'll talk about next and come back to this picture. It's like a stock photo from like Shutterstock. Different types of electronics have current tolerances. So, tolerances will come into very important when we talk about PCB design. If you're making a circuit and you want to turn that circuit into like a thin little green PCB, right? You want to make sure that the wires aren't like short, or in a PCB, you don't want to make sure that the wires are like too tiny and you feed too much current through them, because then your board will catch on fire. Same with like breadboards. If you use too small of a wire and you feed too much current through it, your wire would melt because your wire isn't thick enough to handle that much current. It's not thick enough to handle that much charge, which is why if you are an electrical engineer and you work with like jumper wire that's like 22 gauge, by the way, the higher the gauge, the thinner the wire, or the smaller the diameter, it's like usually this thick, right? Because you don't work with that high of a current. But if you just take a look at wires meant for air conditioners, microwaves, they're like huge, they're like this thick. You can fit like a spider through it or something, I don't know. But the thick wire allows you to pass more current through, and that's the reason for that. So different electronics have different current tolerances. So when we talk about signals, like Arduino can get pretty low-level signals. Basically, the Arduino uses a very low-level current. If you don't know what an Arduino is, it's basically a microcontroller. It's like a tiny computer that's not as powerful as your normal computer, but it can still do a lot of like logical applications, like turning on a light or turning on a motor or collecting data, right? So Arduinos or like computers, they use like 5 milliamp to 50 milliamps, which isn't that big. Amperage, by the way, is the unit in which we measure current from. So again, 1 amp is enough to kill you. That's why we say, that's dangerous. And if you're doing something for a project and you're using motors, you're using solenoids, you're using stepper motors, you're using servo motors, if it has motor in the name or you're powering something that's moving, generally those take a lot of current to move, right? Those are high-powered signals, and usually that will incur having like different types of batteries or power supplies to support this, because look, 3 amps, 0.5 amps to 3 amps. Basically, if you run the current that's going through a motor through your body, again, you'll die. And I'm not joking. Like, it takes like a millisecond to kill you with that much current. And also the voltage, but Now we're going to introduce voltage, and you'll see why. Oh, I have this on a paragraph, but voltage is pretty much the force that pushes the currents through a circuit. So if current was just moving charge, voltage is like a Minecraft piston that pushes the charge to the circuit. So higher voltage would push more charge at a faster rate, if that makes sense, right? So voltage is the force that pushes electrons through a wire. It's similar to potential energy, which is why we call something potential voltage sometimes, or voltage potential, but it's with electricity. Without voltage, there is no current. We'll explain that later on, because, well, it's obvious. Well, I don't have to explain it later. I can explain it now. If you don't have something pushing on it, it's not going to move, right? If I'm just standing here and no one's pushing me, I'm not going to move. I'm not motivated to move because, no one's pushing me to move. That's how charges think. So yeah, that's pretty obvious, but we'll prove it later on. In circuit analysis, there are 2 forms of voltage. And usually when you're analyzing voltage in a circuit, you're going to either use one of these things. Voltage potential, when you see this delta here, usually this means change, right? Change in voltage. So what does that mean? This is the voltage difference between 2 points in a circuit. So in this circuit here, if I was to measure the voltage potential, I would take my multimeter, which is a device to measure voltage, and I put it between 2 points of the circuit, right? And that'll tell me exactly how much voltage there is. And that's usually how it happens, because the voltage potential will take the difference from one point of the multimeter to the other, and it'll subtract that. So you'll end up with a voltage potential, or how much voltage the element you're measuring across is drawing. So in this case, this light bulb, if this was a 9-volt battery, and I put my multimeter here, and this is the positive end, and this is the negative end, what value would I get?
9.
9 is a good one, yes. It is 9, the magnitude of 9. But if I said this is positive and this is negative, negative 9, right? Because this is the negative side. So what I just did there was called polarity. Things have polarity in electronics. It's like really kind of like the number one thing people mess up, because if you switch the polarity, sometimes things blow up. Yeah. So if I was like, okay, if this is my positive end, this is my negative end, and I'll zoom in, it's like kind of hard to see this, but and I switch them, now what would be the voltage?
9 volts.
Now it would be 9 volts, right? Because I'm measuring it backwards. So in this case, I'm measuring voltage potential, but there's another type of voltage called the node voltage. Now, the node voltage is the point voltage at a certain location in a circuit with reference to ground. Explanation is a bit wordy, but all this means is instead of taking the difference between 2 points in the circuit, I'm just going to say, okay, what voltage is at a specific point, like in the top left corner? What voltage is that? Anyone?
9 volts.
It wouldn't be 9 volts. It's connected to ground. So actually, this would be 0 volts. But, we're pointing at a location in the circuit and saying, what's the voltage there? What's the voltage there? We're not calculating a difference. So a lot of students actually mess this up in circuit analysis 1. So you got to know the difference between these 2 voltages. Because when you're calculating stuff later on using Ohm's law and whatnot, that'll become a little bit of an issue.
And also, there's a tip for everybody who's doing IEEE 1101. If the professor gives you a problem and though they didn't give you the reference node, you can choose your own reference node. You can choose your own reference ground. And that will be the point where it's going to be at 0 volts. And this has saved me a lot of time, especially if anybody are taking Ghana or any really hard, like CE1 professor. Like, knowing where to place your reference point for the circuit will save you a ton of time doing work.
Yeah.
So, yeah.
Yeah. So I think Min Kuei is talking about the fact that sometimes you don't get a ground in the circuit. And we'll talk about ground later on.
Yeah, sometimes you don't get a reference point in the circuit, so you can choose your reference point.
Yeah.
Yeah.
We'll talk about ground in a bit because that's a pretty important point. But since we're on voltage, let's go ahead and go back and discuss this picture right here. This thing. So this is a very wrong picture just because usually this doesn't happen. But this is kind of trying to mimic what's called a Tesla coil. Now, Tesla coils usually have these sparks of electricity going out, and you can actually touch these sparks of electricity going out of this metal dome. And it doesn't kill you. And why is that? Because in Tesla coils, where you see this type of electricity happening, usually there's a lot of voltage, but there's only a very tiny amount of current. Because voltage is the force that pushes current, right? So basically, it's pushing this current really fast through this gap, so it jumps the gap. Now, usually, this big of a gap doesn't get jumped because, the farther you are, there's a whole equation to describe this, but it's pretty much quadratically, or it's exponentially decreasing based on the radius or the distance you put these two wires. So, but the basic concept of Tesla coils, it pushes a lot, but there's very little current, so you can probably touch this and still be fine. They sell these as toys nowadays. Like, you go on YouTube Shorts and they're like having advertisements of people sticking shrimp and other phones and other chickens on these Tesla coils and selling them. It's a hazard. It just for people who don't know how to use it, it looks cool, but one little shock and you're dead. This is by no means to discourage you from electronics, by the way. It's awesome, but just in general, be careful because it is a dangerous profession. All right, next is ground, and now we'll get into why this matters. The ground is like a reference point in your circuit, like we've talked about before, right? Common ground is needed in circuits to represent a reference point, or when you're building a circuit diagram, you say, okay, this point is 0 volts, right? The reason you need that is because that's how you calculate literally everything else. It's how you calculate voltages in a circuit. It's how you calculate resistances, When you use Multisim or any other program like that, most of these programs will not let you simulate a circuit without a reference ground. It just won't let you. It just won't work. And also, another common problem in many introductory students is they forget the ground in their simulation. And then they're like, oh, why is my circuit not working? Because you don't have a ground. Your circuit doesn't know where to calculate 0 volts from. So if you're doing electrical stuff and you're simulating it especially, make sure you know where your ground is. And also, in the real world, where is ground anyways? The ground, the literal ground, yeah. So, they're saying the easiest way to protect yourself from being shocked is just to wear shoes that protect you from the ground. Because if you have rubber soles and you touch the ground, and let's say you put your hand on a live wire, you're not going to get shocked. Because the way you get shocked is you complete the circuit. The only way for a circuit to complete is if it goes to ground. So if I took off my shoes and I walked barefoot all the ground and I touched the live wire, I'd be dead. Because the current's going to go through my body, through my heart, and into ground, and I'd be a piece of fried chicken. But, so, having rubber-soled shoes is already a good way to protect yourself against high electricity, which is why a lot of electricians wear big rubber boots to protect themselves from that. Because even the ground in the earth is dangerous. Also, I think this should be said because we're talking about circuits, but don't stick a fork into an outlet. Don't get encouraged from this workshop and go stick forks through an outlet because it's you're shorting the live and neutral wire and just not good at all. And you don't want to do that in general. And it's the number one. They have baby proofing outlets for that. It's don't stick forks in outlets. I think it should be said.
Also hide your fork somewhere that the baby can't get to them.
Yeah, to higher forks.
Because even though if they couldn't put it in the socket, they could still take it and snap somewhere with it.
Yeah. Oh yeah. All right. So we've talked about current. We've talked about voltage. In electricity, there's the 3 main pillars of things we look towards, and the third one is resistance. Resistance is just a coil of jumbled wire inside of this plastic encasing that prevents current from going too fast, right? Because if we didn't have resistance and we just had a circuit with voltage and we have current, there's a saying in electricity that current always follows the path of least resistance. So, if your body is like the least resistance connecting the power outlet to ground, it's going to go through that. But resistance stops that from happening if you put it in a circuit. So, if you don't have a resistor in your circuit or you don't have a means to stop that current, it's just going to go faster and faster and faster until your circuit blows up. Another common mistake for like introductory electricians is not putting a resistor in combination with like an LED or something like that, because you don't want to have too much current. Resistance is what pushes the current back down. It says you stay in your place, don't go too high, don't blow up the circuit, and that's what that is. Again, just a bunch of wires smashed together to create resistors. Probably a better description here. So it restricts the flow in a circuit and comes in the form of resistors, although I think that should already be said. And higher resistance means less current. So if you have a really high resistor, you have a very little current passing through it. Does anyone know here how much current or how much resistance is in the human body? Any guesses?
1 than 5.
1 to 5?
More than 5.
More than 5. Well, you're correct. It's more than 5. But exactly how much does it go up to?
100 ohms.
So it's anywhere between like 10,000 ohms to 10 mega ohms. And it all depends on how dry your skin is, right? If you like put your hand in soapy water, like don't go near an outlet, you'll shock yourself. But the human body generally has a lot of resistance. But we are a resistor. We're one of these. Nothing we can do to stop it, right? Electricity can pass through us, which is why it's really cool. There's circuits that activate when you touch it, because those are called touch capacitive circuits, and they activate based on the fact that our bodies are basically a resistor. But very low amount of current can actually go through us because of how high resistance we are. So this little triangle here is the pinnacle of all electrical engineering. You should memorize it because it's cool. Even if you're not an electrical engineer, memorize it. This is Ohm's law. Ohm's law states V equals IR. I like this picture because it has equations. And it shows the relationship between voltage, current, and resistance, because they're all interconnected and they're all related, and you can describe almost everything in ECE with it. So the basic equation is V equals IR. And the way you use it is pretty much based on what you want to calculate in this triangle. You just put your hand over it, right? If I want to calculate voltage, I cover the V with my hand, and then I remain I and R on the bottom of the triangle. So I multiply these together, and I can see that I times R is equal to V, right? This tells us that voltage is equal to the multiplication of current and resistance. So what does this tell us exactly about the relationship? If we just look at the equation up here, we can set some things as constant and take a look at the other variables to see how they relate to each other, right? So if I say voltage is constant, I give the system a battery, and the battery is 9 volts, and I'm not going to change that. And this is kind of like algebra here, so it should make sense. If voltage is constant, then what is the relationship between current and resistance? If I increase the current in a circuit, what happens to the resistance? If I want to keep the same voltage. So this goes up. Yeah?
Resistance goes down.
Resistance goes down, right, yes. So if one thing goes up and the other thing goes down and they multiply with each other, what can you say about the relationship between those two? They're inversely proportional, right? So usually you don't change the resistance, you change the current instead. So in a circuit, if you have constant voltage, then if you increase the resistance, you'll get less current. But if you decrease the resistance, you'll get more current, right? Which is why if you have a lower resistor, you'll get more current. Kind of makes sense that way. But these other two equations down here are variants of this top equation, Ohm's law, right? So if I'm trying to solve for current and I have voltage and resistance, then I can cover current with my right hand, and I get V and R, but V is on top and R is on the bottom, so it looks like a fraction, right? If you cover the I with your hand, then V and R are like this. So if current is equal to voltage over resistance, what can you say about the relationship between voltage and resistance? So let's do this example again. If the current's going to be the same in my circuit, and I increase the resistance, what happens to the voltage? Will it increase or decrease? It will increase, right? So if I increase the resistance, the voltage will also increase. If I decrease the resistance, the voltage will also decrease, which means what's the relationship between voltage and resistance? It's a direct relationship, right? Cool. So we know that the relationship between current and resistance is inverse. we know the relationship between voltage and resistance is direct. Now let's take a look at the last one. What's the relationship of voltage and current when resistance is constant? So if we want to solve for resistance, we'll cover up R with our right hand, and we can see that V and I form a fraction, right? So resistance is equal to voltage divided by current. So let's do this example. If my resistance is constant, and let's say I increase my voltage, what does the current have to do to keep the resistance the same?
Increase.
Also increase, right? Same thing. If I decrease my current, what happens to the voltage?
Decrease.
Also decreases, which means the relationship is? Yeah, okay, now we understand Ohm's law. So in any application in circuitry, you can always relate back to this because you then understand what the relationship between these three characteristics are, right? As a quick review, just so you don't forget, current is moving charge, right? Moving electrons through a wire. It can move very fast, it'll get very hot. It can move very slow, that's like low current, right? So current is just moving charge. Voltage is the force that pushes that charge, kind of like a Minecraft piston, all right? Or just someone behind you pushing you forward, right? Resistance is the thing stopping the current from going too fast. It's kind of like a little tunnel that the current must pass through, and it slows them down. And any kind of wire can act as a resistor. It doesn't have to be one of these things. You can have a very, very long wire, and that can act as a resistor. Because all a resistor is just a coil of wire, right? That slows charge down. So if you have a very long wire, that very long wire may have some resistance. Keep that in mind, because if you're working on some like power or some electrical stuff, that may come in handy. And when you figure out like, oh, why am I not getting like this amount of current? Why is something like lagging behind? It may be because your wire is too long. And there's a whole equation that can explain why. But if you want more current, just like make the gauge of your wire thicker. Which is why, again, like if you have a microwave or air purifier or a heat gun or anything that uses electricity to transform it into something else like heat, they usually have thick wires powering them. All right, so now that we talked about Ohm's law, let's go into circuit components. So when you're getting interested in circuitry, what do you get for, usually buy like a really big value pack of electronics off Amazon, or shameless plug, you go to the circuit construction workshop next week, sign up for it. But let's go over the common circuit components that you'll find in one of these packs, like how you begin to learn circuitry and build them. First thing is resistors. Well, you already talked about these, right? Like, you know what they do, right? Anyone? No, Yash? No? What do resistors do? It resists the flow of current. That's a brilliant explanation. Yes, exactly. It doesn't let the current go too fast and destroy our beautiful circuit. By the way, resistors can catch on fire, and they can heat up, and they can burn your hand. Yes, Sean. Yes, they can burn your hand. So you gotta watch out for them. Yeah. What's up? Huh?
Once we can't hear you probably.
Oh. Sorry guys. I got too excited. So resistors resist the flow of current, which is why you got to have them in your circuit, otherwise your circuit will blow up. So it also protects against short circuit. Now the term short circuit just means a circuit or a bunch of wire without any high resistance. And a short circuit is bad because, if you don't have any resistance, what can happen when you put two wires together, you can get sparks, you can get fires, you can have too much current going through your circuit. So short circuit just defines a part of the circuit with zero resistance. That's usually bad. You don't want that. You don't want stuff blowing up. Not good. You can also control currents, right? Also very good at controlling currents. You can use it to regulate voltage, which is a good one because remember what the voltage regulation comes in the form of voltage dividers, usually when you're working with resistors. And you can use Ohm's law to decide on what values of resistors you can use to chop that voltage down in half. And you can use it to redirect signals. I wish I had a diagram for this. Pull-up and pull-down resistors are very useful in microcontroller programming. When you're working with digital logic, which we'll talk about later today, you need pull-up or pull-down resistors to be able to give the microcontroller some idea of like if you're working with a 1 or a 0, a high or a low signal. Because sometimes, like with a switch, a switch works like, a switch connects 2 points of a circuit together, right? So let's say we want an Arduino or a microcontroller to detect if a switch has been connected, right? And if a switch hasn't connected, let's say the other end of the switch is like 5 volts or something, the microcontroller doesn't know what the end of this wire is because it doesn't know if this is a 1 or a 0 because it doesn't have a value. It's not pulled down to ground. But once you connect the wire, 5 volts goes straight to the Arduino, and the Arduino says, oh, hey, I know that's 5 volts. So if you want accurate measurements or accurate results in your microcontrollers when you're doing robotics, you need to make sure you have pulled up or pulled down resistors. Pull up resistors go up to 5 volts or some like VCC value, and pull down goes down to ground. That may sound confusing to some of you, but if you ever work with robotics and Arduino, this will make a lot more sense. Capacitors. Oh, I love this video. Do I have sound share? Okay, so before I go over what capacitors are, I'm just going to share this short little video with you. The capacitor will short itself on itself because it's 2 metal plates. When the metal plates touch, they will short each other, and the current in a short circuit will send itself to infinity. However, this power source is currently rated at 10 amps, so it won't do that. I'm just going to stand back here and turn this off so it doesn't blow.
All right, buddy.
Here we go. 3, 2, 1.
Oh my god.
All right, that was it.
Ooh.
Were those ceramic?
No,
No.
electrolytic.
Oh.
So what you just saw there was a capacitor exploding, and usually, you know, I wish I had that on the surround sound audio because it would be more like boomy, but I did that last semester and it kind of scared off some people, so I'm not going to do that. Anyways, these are kind of the most volatile components in electrical engineering when you're building circuits, just because, again, they can explode. But that's not usually when you use them on like a regular basis and you don't abuse them, they won't explode like that. It's just fun to see stuff explode. And this is kind of like the safest ways to do it. This kind of plastic cover, by the way, it blew a hole straight through it. So you never want to put your hand above a capacitor because it'll blow a hole straight through your hand. Fun, huh? Anyway, so what the heck are capacitors anyways? Capacitors are made out of 2 little metal plates on each side, and they store electric charge, which means they're kind of like a battery, but you know, they don't store charge using chemicals. They store it using electric plates. So capacitors are used for a wide variety of applications, but the most common applications they're used for, at least in like introductory circuits, is to be used as a buffer. Basically, you put a capacitor across a noisy signal to make it like really fine. And what I mean by noisy is sometimes when you're trying to read from a sensor or like an output object, or you're trying to like read from like, you're trying to read important data, right? And you want your important data to come in at like a really fine streamline like this, right? It's very steady. You want data to be like that because you can read it easily, right? It's like a book. If you're reading a book, you want the book to be stable. You don't want the book to be moving. But sometimes, based on what happens in the circuit, your stable signal can get messed up. You know, anything can mess up a signal. Kind of like you can have noise around like magnetic fields. You can like shake it, it'll mess up the signal. Anyway, a lot of stuff can mess up signals, which is why your very steady signal starts to look like this. It starts to, you know, have a seizure. And the way you calm it down is you use a capacitor. You put the capacitor over it, and it calms it down and makes it steady again. The analogy I'm going to use for this is like if you're reading a book and someone just like comes, grabs your book, and starts shaking it. You're not going to be able to read a thing, right? Kind of the same thing. You want to put a capacitor. I don't have an analogy for capacitor in real life. Just like it makes your book stable, right? So you can read it again. So capacitors are put across noisy signals to make them stable. And you use them in voltage regulators. You can use them in PCBs for design. You can use them in like data when you receive data from like a temperature sensor. Yes?
Would you say capacitors like dampeners?
They are kind of like dampeners, yes. But they don't actually dampen any voltage. They just like filter it. I think that's a better word.
Filters.
Filter is a better word, yeah. That's the other application for capacitors. They can make filters. If you put a lot of capacitors together, and by the way, if you link capacitors in parallel, which means you can put capacitors one after the other, you can make a supercapacitor, right? It's just a bigger capacitor. It can store a lot more charge and has a very, very high discharge. Usually in batteries, you don't want them to discharge like 50 amps into your little toy truck, right? Because that wouldn't be fun. But supercapacitors, like, they really don't care about that. They're used for applications in which you need very, very high discharge. So they can shoot a lot of current into your motor, or a lot of current into your RC airplane, or a lot of current into your flying robot. Doesn't matter the case, but supercaps are used for that application. But, overvolting a capacitor will cause it to explode. Capacitors have ratings too, right? Based on the size of the capacitor and the plate size and the farad rating, because capacitors are measured in farad, if you exceed that voltage rating, it'll explode like you saw in the image. This, I think, was a 15-volt capacitor, and I set my power supply to 25 volts. So, cap go boom. Again, applications and circuits, you can put them to reduce noise, stop the book from shaking. You can have them for timing sequences, which is also a good one when you're working with 555 timers, because for 555 timers, those are like the most common like adjustable clocks and circuits. You need to put a capacitor there which tells it at which rate it oscillates. So different little timing sequences there for you. It's basically a repeater from Minecraft. Wait, when was this? 6:45. Oh, it's now. Yeah, basically. The capacitor will short itself. Okay. Well, I'm going to move on to inductors to talk about this for a second. We're not going to go too deep into this yet, but inductors are pretty much storage devices, but it's a little bit different. It's instead of storing energy as electricity, it stores it as magnetic fields. Common inductors are the ones found in motors, which can come as brushless or brushed. Pretty much motors spin, and they use the magnetic fields to activate that spinning motion. You can also find them in microwaves, light bulbs, solenoids, and wireless charging. We talked about wireless charging earlier in this lecture, right? You put your phone on this little plate, it charges it. How does that work? Well, to keep it simple, there's two types of electricity. There's DC electricity and AC electricity. DC is direct current. Pretty much current only goes in one direction. AC, it goes in two directions, right? It moves forward and then moves backwards, right? The reason for AC to exist is because of power lines. Getting high power to your home, like 110 volts, that takes a lot of energy if you're doing it the DC way, which is why if you have a lot of current just moving back and forth a lot over like high power lines, it saves you a lot of energy, and it's cheaper, and it gets power to you the same way. So two types of electricity here, but for wireless charging, what it does is it turns DC electricity into AC, such that the AC signal, when the current moves like back and forth like this, it activates current. Basically, the current activates magnetic fields inside inductors. And these magnetic fields are able to transmit power wirelessly through the air into your phone, which has a receiver coil that turns the AC back into DC. So pretty much, it's magic. Not really. So diodes. Diodes are fun because the most common diode you'll know in electrical engineering is the LED, the light emitting diode. Everyone knows what an LED is, right? But diodes allow current to flow in one direction and prevents the flow of current in the other direction, right? So in this case, if we put current through this way from the left, then it will allow it, right? This is called forward bias. But if we put current through the back, if we put it through this way, this like little line acts as a shield. It doesn't let current through. So, that's a reverse bias. It doesn't actually let a current go through. And this diode is actually really, really important in electrical engineering to prevent something called reverse polarity. So diodes normally have two terminals. We call them the anode and we call them the cathode. The anode is on the positive side and cathode is on the minus side. A little bit different from chemical engineering if you guys are in that major. So forward bias in diodes allow current to flow through correctly, but if it's in reverse bias, it prevents current from flowing. Breakdown happens when too much voltage in the reverse direction breaks the diode and allows current to flow in the other direction. So breakdown is a pretty interesting mode, but you can kind of relate it to like a dam, right? A dam is just a wall that prevents water from going out. Have you guys ever seen a dam break?
Yeah, it's like when you move the door, it just pops open.
Yeah, it usually happens because there's too much pressure on one side or a defect in the dam or something like that, but that's what breakdown is. Pretty much there's too much on one side and it just breaks through like this kind of protection mechanism and allows current to flow through backwards, and that's really, really bad. But luckily for us, breakdown usually doesn't happen unless you have like an exorbitantly large amount of voltage happening from the other direction. Kind of like 200 volts or something like that. It's like insane. For applications, the first one, and the most important one, is reverse polarity protection. I talked about this last time when we talked about coding, but if you're designing anything to be used by someone else, you always got to assume that they're stupid and dumb because, they'll find a way to mess it up. If I build a circuit for someone else, right, I'm going to just assume directly that they're going to find a way to blow up the circuit. Easiest way, connecting the battery backwards, right? Because that's not good. If you have battery connected backwards, that means your current's flowing in the wrong direction. That destroys chips, that destroys transistors, that creates short circuits. It's just very, very bad. Now, the way to prevent against that is to just add a single diode in the mix. Because if you connect the battery backwards this time, it won't allow current to flow in the other direction. It stops it, which protects the circuit. All your hard work isn't lost. And I can say that I made this mistake once when I designed the first ever Blinky Learner 1 for the soldering workshop. I didn't put reverse polarity protection because, I was just not thinking about that. Yeah.
I burned my chip by accidentally switching it on the Blinky Learner. And then I had asked for a new chip. I wasn't looking too hard because I usually assumed there's the reverse polarity protection wasn't there.
Yeah. So Mansha connected the battery backwards because usually I put. Also, you got to put a lot of fail safes to make sure the user doesn't screw up. But I guess we didn't have enough on the first version, so a lot of chips got burned because people connected the battery backwards. And it was totally my fault, by the way, because I didn't design that. But on the second version, I put the diode back in, which now I always put a diode just because you got to protect against the circuit. So yeah, that's the reason for that. Protect your circuits. Don't let people blow your circuits up. You can also use them for flyback diodes. Now, flyback diodes are a little different type of diode you used in motors, right? And the thing that protects is voltage spikes and current spikes. Because when you stop a motor from moving, it's an inductor. So inductor is kind of like the large water wheel. It has momentum. So if current goes through it and you have immediately stopped the voltage, current can't stop immediately through an inductor. That's one of the fundamental properties of it. So, it'll shove more and more current through it and cause a spike in current and voltage. Flyback diodes prevent that by feeding the current, the excess current, back through to the beginning of the motor and just creating a loop. That's why it's called flyback, because it flies the current back. But it's really important in protecting the circuit as well, which is why we use it a lot. Diode clamp is another one, but I won't go too deep into it. You can Google that if you want. Transistors, also a very, very incredibly important part in the history of electronics because your computers wouldn't exist without transistors. Actually, this is kind of like what we're going to do to transition between you talked about electricity into talking about digital logic, because when we talk about digital logic, now digital logic uses zeros and ones, and that's what transistors bridge the gap between. So transistors are electrically controlled switches. There are two main types of transistors that we're going to be talking about. A BJT is a bipolar junction transistor. It's a current-controlled switch. It was the first ever transistor ever made. So back in the 1980s, 1975s, they had big BJT transistors, which use current to act as a switch. So I won't go too deep into transistors, but there's 3 terminals, and 2 of them will connect if you feed current into one of them. FETs, or FETs, or MOSFETs, are field effect transistors. These are the good ones. These actually came out around 2000, 2005. So they're fairly recent transistors, and they're really important to us because they're a voltage controlled switch. We don't have to deal with current, right? So as long as we feed a voltage into one of the pins, 2 of the other pins will connect. And that's why it's an electrically controlled switch, because we can use an Arduino or some other method to open this up and allow for higher current and higher applications to be powered by it. And we'll talk a little about transistors later. These can be used for step up and step down voltage controllers. Again, if you are powering something like a motor and the motor is regulated for 12 volts or some really high voltage, and your Arduino only has 5 volts, with the thing that you're controlling it with, you can't power the motor with an Arduino because it just isn't possible. It's not powerful enough. So what happens is you put this MOSFET in between the Arduino and the motor, and you basically say, okay, Arduino, I'm going to go ahead and feed a 5 volts or lower voltage into one of the pins of the MOSFETs, and then the other 2 pins will connect and power that really high voltage motor, right? So great for low-level triggering of electronics. And also, it's an entry into digital logic, which it's really cool because digital logic, we work with TTL, which is called transistor logic, and CMOS, which is complementary metal oxide semiconductor, I think. My memory's not treating me too well. But pretty much, we can boil down the output of the transistors into a 1 or a 0, which is pretty much where the two things bridge, right? 1 is going to be 5 volts, and 0 is going to be 0 volts, right? So either I feed a signal into the MOSFET or I don't. And usually, you have to like worry about anything else. When we talk about digital logic, we're just talking about digital, which means there's only two options, which is called binary, which is either a 1 or a 0, right? There's no other option. So let's get into protection circuits. How much time do I have?
An hour.
Wow, okay. Let's speed through this a little second. We talked about reverse polarity protection already, so I'm going to breeze through this slide. Pretty much, if your user connects your battery backwards, you don't want them to toast your circuit, which happens more than you think. It's like some circuits aren't designed with RPP, so you're going to suffer. So just be careful when you're using electronics because you might encounter something that doesn't have reverse polarity protection, and then your entire thing starts smoking and burning, and you're like left wondering why. You just wasted like $35 on this receiver that didn't work, based on a personal story. So you can protect against reverse polarity protection by just putting a diode. This snippet is from a circuit I actually made, and I put the diode right here just to prevent current from going through the backwards direction. The bad thing about this is because diodes usually have what's called a turn-on voltage. And turn-on voltage is like 0.7 volts, right? And if you have a diode, pretty much it steals 0.7 volts from your power source, which is not good if you're using something that has very low voltage. Let's say you're powering a circuit with 3.3 volts for wireless communication. And you don't want this diode to be there because that will bring that voltage from 3.3 volts to like 2.6 volts, right? And that's not good because it's not enough for that wireless communication. So how do you prevent this diode from sucking up so much voltage? You don't have a diode at all. This is the PMOS method, which allows you to have reverse polarity protection without having a diode there. And it just uses a transistor, which prevents voltage from or prevents current from going in the other direction. So the simplest explanation of this is pretty much this pin right here is the gate of the MOSFET, and pretty much if this gate is 0 volts, right, and its normal application this gate is 0 volts, it'll let current through. But as soon as the gate is 5 volts, this will close up and prevent current from going in the other direction, right? So if you don't want unexpected behavior to occur, you can use the PMOS method instead. However, the con of this method is that it's actually more expensive than the other one than just putting a regular diode. So for most cases, just a regular diode would work. But just introducing you guys to more complex stuff. Regulator circuits. Now, the idea of regulation in projects is important, right? When we talked about Hyperloop Mini and powering like a robot, sometimes the motors in the robot need higher amounts of voltage than the brains of the robot. Like I need more energy to run a mile than it does for me to do a math test. Some of you guys might disagree, but kind of like that application where the motors need like 12 volts, the microcontroller needs 5 volts. You can't just plug 12 volts into something that needs 5 volts because it'll explode, right? Into like thin strips of iron in the air. So there's a few ways to regulate that high voltage down so that it's reasonable for you to, understand. This is the most basic chip used for lowering voltage down to something that can be tolerated by an Arduino, which is the LM7805 chip. These are like dual inline packages. They're not dual inline packages. They're TO220. I don't remember the name for it, but it's a type of package that's packaged inside of this chip, and it's very, very common. You just use it in this configuration to get your 5 volts. Like you can have 12 volts here, you place it across this, you immediately get 5 volts. It's pretty simple, pretty easy to understand. This is called a linear voltage regulator. These capacitors here, again, remember what they're for? Yeah, noise reduction. Because, if this 12 volt source has a bit of noise, you're really shaky, like a shaky book. You want to use these capacitors to smooth it out, right? You want to bring it down to a smooth value so that the regulator can do its job and bring it down to like 5 volts. This is known as a step-down regulator. That's what's inside that chip, by the way. So if you want to know everything that's inside the chip, there's a bunch of transistors here that get smushed down inside this package and gets manufactured by like a laser in order to do the job. But unless you want to get into chip making, you don't need to understand this. All you just need to know that everything here turns higher voltages into lower voltages. And in this case, it's exactly 5 volts. Here are a bunch of chips that may or may not, well, they do the same thing. They regulate voltage, except this time, these are adjustable voltage regulators. Or your output is not locked to 5 volts. It can vary between 1.25 volts to 35 volts of regulation, as long as you put in something higher, right? You don't have magic voltage multipliers yet. These chips can handle different amounts of current draws, which is important to note when you're using these things, because sometimes you want to draw too much current from it. Like, let's say you're powering a solenoid from one of these chips, which uses like 5 amps, but this can only support 1.5 amps. So these series of chips, and chips have these things called families. They're kind of like our real life families, except they don't actually have any relationship with each other, except for properties. This family of chips is adjustable voltage regulators, which means it can turn very high voltages into like low voltages. But they have different properties, which are the amount of current you can draw from each of them. So the LM317 can support 1.5 amps, which is good for like a few solenoids. But if you want more current, you just have to go to a bigger chip. And if we go up the ladder of chips, you can draw 3 amps, you can draw 5 amps. It also gets more expensive. So the chip price is kind of large. If you want to know what the output voltage is going to be, it depends on these 2 resistor values right here. And this is the equation to get this. So, if you want some weird voltage that's not 5 volts, let's say you want to regulate down to 12 volts instead, then you would go ahead and just run some resistor values through this calculation to see exactly what it can support. It's all based on ratios. This AMS117 is the most popular SMD voltage regulator I've ever seen, and they come in 2 different flavors. You have fixed voltage regulators, which the output is fixed, and the adjustable, which does the same behavior as we previously stated. But, it's good for like smaller application, and it's basically the gateway chip into SMD soldering if you want to, solder very small objects, because it's very big, it's very large, and it's not that difficult to solder. Even a baby could do it probably. I wouldn't let them near a hot iron though. So, it's kind of the same behavior. Again, you want to put capacitors here just to make sure that noise isn't an issue. Okay, full bridge rectifier takes AC and turns it to DC. I'm not going to go too deep into it, but that's the circuit for it. Okay, good. I wanted to get to logic gates because that was the main core of today, what we're talking about today. So again, in history, we've turned to computers, and all computers are made out of billions and millions of transistors inside of it. There's this thing called Moore's Law that states that every 2 years, the amount of transistors on a chip will double, on a chip or on a board, on a motherboard, will double, and the size of the chip or the footprint of it will shrink by 2. Now, this hasn't really happened. It's not like an exponential growth anymore. It's more of a logarithmic growth where it like flattens out. But in general, since like the early 2000s, we've gotten more advanced computers, more advanced technologies. Like our computers don't fill up a whole room anymore, right? So the development in computer architecture and computer engineering in getting those transistors to be small and getting that logic to work more precisely and more accurately is pretty much the logic gates are the basis of that. So understanding this is kind of like your foundation for actually making a computing system to work. So working with logics, you don't use voltages anymore. So take everything you heard about voltages and just like don't worry about it for like the next hour. So we'll call high as like a 1 or a 5 volt signal and low as a 0 volt signal. It's always going to be 0 volts, right? Low is always going to be 0 volts. Low is always going to be 0 volts. But high might not be. High is usually 5 volts with an Arduino or 3.3 volts using an ESP32 or a Raspberry Pi. These are cool. It's kind of like mini computers. Actually, they are mini computers. You can connect them to Wi-Fi. You can run an operating system on them. It's very cool. And you can work with logic gates to provide expected outputs. The following are the most common logic gates that are the foundation of everyday computing, like the AND gate, the OR gate, the NOT gate, the NAND gate, the NOR gate, the XOR gate, and the XNOR gate. This applies to computation arithmetic units and computer architecture, but just understand that they're the basis of how your computer works. So the AND gate, we're going to talk about this first, right? The AND gate, runs the AND application. If you already know how to code, this should be pretty simple. If you don't know how to code, it's okay. It's not too difficult to understand. Pretty much, it's a chip with 2 inputs and 1 output, right? And the 2 inputs, if we just take this one chip, for example, has 4 possibilities or 4 combinations, right? Think about this. If you had a combination lock with only 2 inputs, and inside that safe that the lock is protecting, you had $1 million, and you really wanted to get that, right? It'd be pretty dang easy to crack the combination by just trying all combinations. So, and that's what we're concerned about here. If we have 2 inputs, the amount of combinations we have are going to be 4, right? Anyone know the equation to calculate that?
Yeah.
2 to the n, right? So, based on the number of inputs you have, which is n, you take 2 to the power of that, and you get the number of combinations on the left, right? And in this scenario, if we just ignore the output for a second, we can go ahead and generate a list of combinations by taking the lowest value, or lowest, the LSB, which we call the lowest bit, and we just go 0, 1, 0, 1, and we just keep repeating that all the way down. And then on the next column over, we do 0, 0, 1, 1, and then on the next we go 0, 0, 0, 0, 1, 1, 1. It's a repeating pattern that generates all the combinations. If we have 2 inputs, the combination is pretty easy. It's just 0, 0, 0, 1, 1, 0, 1, 1. There's 4 different combinations. So the AND gate will give you an output of 1. It will work, right, if the inputs are both 1. It's kind of like saying, and I was thinking of how to deliver this. Pretty much, if I told Mancha to go out and go to McDonald's and get me an iced tea and an ice cream cone, right? I would only be happy, and I would only say, yes, I'm happy with this, if she comes back and gives me both of those items, right? Even if she forgets one, I'll be bad, and I'll go, where's my iced tea, Mancha, right? So it'll only output high, and it'll only say yes if both the inputs are yes, and that's what we're looking at here. AND gates are very fundamental in all of the logic, right? So as you can see in this table here, the way we look at this is all the inputs, 0, 0, it'll say 0, unless, like 0, 1 will be 0, 1, 0 will be 0, unless both the inputs are 1, and then the output will be 1 as well. Does everyone get that? Cool. The OR gate, now there's a few of these gates we're going to go through. Now, if I told Mancha to go to McDonald's and get me an iced tea or an ice cream cone, because I know that sometimes McDonald's ice cream machines don't really work that well, I'm going to say, as long as you get one of these, I'll be happy, right? And Mancha comes back and gives me an iced tea, but says, sorry, the ice cream machine broke. And I'm like, okay, that's okay, because I said or, right? I didn't say and. So if either one of these inputs is a yes or a 1, then the output will be a 1. Boolean equation is a plus b. But if we take a look at this truth table here, we can see that 0, 0 is 0, because both inputs are like no's, like zeros. The next one is 0, 1. So if A is the iced tea and B is the ice cream, then basically this combination says that Mancha got me the ice cream, but not the iced tea, but I'm still happy with it because I got 1, right? Next combination is 1 and 0, that gives us a 1, and finally, if I get both of them, I'll be overjoyed, but nothing special will happen. So the output is still 1, I would still agree with her, right? So that's what the OR gate is like. It outputs high when at least one input is high. The NOT gate. So this is like the third gate that we're going to deal with. NOT gate just does the opposite of what you give it, right? So it's an inverter. So if you put in a 0, you'll get a 1, and if you put a 1, you'll get a 0. It's a weird gate. But the Boolean equation is not A equals B, it looks like this. If you go into digital logic in more advanced level, you'll start doing things like Boolean algebra, which is a lot of fun. It's kind of like regular algebra, but a little more confusing because you're working with digital logic. But in this case, this is an inverter, it flips the signal, and it does cool stuff like that.
Oh wait.
Yeah.
Does anybody here know Minecraft Redstone?
Minecraft Redstone. Does anyone here know Minecraft Redstone?
Because like if you guys do, then I could make some really useful comparisons. But if you guys don't, then
Yeah. So, I started from Minecraft Redstone too. You can make all these gates in Minecraft.
yeah.
Yeah. I think one person on Zoom is a Minecrafter. Brayden said yes.
We have a game night where we do this in Redstone.
We can do that.
Yeah, sure.
You guys want a
And
game
to
night?
learn how to use Redstone, that's the one area of Minecraft that I'm too scared.
A workshop on Minecraft Redstone.
I will take that.
I will take that. To be honest,
Okay.
but I will take that. That's a good idea for
I
next
feel
week.
like a lot of people.
Okay.
I can support you.
All right,
because I
all
don't
right.
know, like, I need to watch like some of the old like mumbo jumbo videos.
Maybe we'll do a game night one day where we do Minecraft Redstone all night. I'll talk to Boric about it. Yeah, that'll be fun. Really called me out on that. Sorry, Brayden.
I forgot to build I forgot how to build a 3x3 just indoor now. I'm like rusty as heck. Oh my gosh.
Yeah. Yeah, no, like Minecraft's cool. Like a lot of like the stuff that we talk about today does have comparisons to Minecraft as well.
Especially like if you are even like doing like modded Minecraft, there's a really cool mod called Create.
There's also one called Immersive Engineering and does power stuff too.
Yeah.
Yeah.
Let's move on.
Yeah. All right, moving on. NAND gates. Okay, now we're going to the gates that are the basis of, well, pretty much when you're working with transistor logic, there's no such thing as an AND gate, there's no such thing as OR gate. Everything in the world is made out of a NAND gate, or the next one we're going to talk about, a NOR gate. They are called universal gates because you can make everything, you can make all the gates with NAND or NOR, right? Because you can make inverters, you can make AND gates, you can make OR gates, you can make XOR. You can make all the other gates we're talking about today with just a NAND gate. So just understand this, inside your computer, it's all made out of NAND gates, right? Now, the NAND gate is pretty much a AND gate and an inverter, right? Smushed together. And pretty much what happens when you have this kind of system is you're flipping the output of the AND gate. So if the AND gate had 1, 1, and 1 at the bottom, now everything is flipped, right? And if you have 0, 0, you get 1. If you get 0, 1, you get 1. If you get 1, 0, you get 1. And if you have 1, 1, you get 0. So everything is flipped. It's a kind of weird logic and kind of make a good comparison to it, but you can make all the other gates with it. This is what it looks like if you build it out of transistors. And this is what you would find when trying to make all the other gates with just NAND. Right? It's a cool experiment in comparing the properties of each gate. Like an inverter is just like this, you're connecting it to itself, or you use 3 NAND gates, and you use 2 NAND gates, XOR and NOR, it's this configuration. I would suggest memorizing this because it impresses people who know about digital logic. XOR.
Exclusive OR.
Yeah. NOR is kind of like NAND, except it uses an OR gate instead of an AND gate. So think about the OR truth table. Oh, did I ever say that these truth tables? They tell the truth, right, about what the gate is. They're called truth tables. So in this case, in this scenario, it's kind of like the OR gate output, but flipped. So this time, 0, 0 will give you 1, but everything else will give you a 0. So basically the rule for this is as long as there's a 1 in the input, the output will be a 0, right? And again, this is useful because the NOR gate is the other universal gate. So it appears in all the computers. And again, if you memorize the configuration of this, everyone will love you. XNOR. Okay. Now, XOR is going to be very, very important, and the behavior of it is also very, very, very important, because without it, pretty much we're not going to get to where we are today with internet security and concerning about cybersecurity in general. The XOR gate is a little bit weird. The rule is as long as there is an odd number of inputs, right? Odd number of yes inputs, it'll give you an 1 at the output. So in this case, if I have an odd number of 1s on the left side, then I have a 1 on the right side. So in this case, 0, 0, there's no 1, so it's going to be 0. 0, 1, there's 1, 1, so there's going to be 1. 1, 0, there's 1, 1, so the output's going to be 1. And on the last line, we have 1, 1, which is 2 1s. Everyone's on Zoom is probably confused right now. But since there's 2 1s, that's an even number, which means the output is 0. Now, the reason I say this is cool is because XOR is kind of like the basis for encryption. Encryption is the action of scrambling data so that people can't see it because, security, right? You don't want to give your password to your safe of $1 million out to anyone because, they'll steal it. And people are motivated by what they can gain for free, So you've got to protect things that you want to protect. And one of the earliest ways to protect against data was using XOR. XOR, it has a funny little property where if you scramble the data with a key, if you XOR the data with the key, the output will look like a scrambled mess, right? But if you XOR the output with the same exact key, it'll give you back the data. Analogy is kind of like the same thing as if you had 2 keys to your house and you gave 1 key to the friend that you trust the most, right? That's how you're able to communicate data using the XOR algorithm or XOR encryption algorithm. But just in general, for your understanding, this is the truth table of XOR. Remember that's an odd parity checker, and it'll only output 1 if there's an odd number of input 1s, right? Now based on this logic, what do you think the XNOR gate does? The inverse of this. Any guesses?
Even number of ones would produce an output.
Yes. Well, kind of, but yes. So it would be an even parity checker with the exception that 0, 0 gives you a 1. Because I guess 0 is an even number now. But it will output high when there are an even number of high inputs with 0, 0 as an exception. And the Boolean equation looks like this, and this symbol kind of looks like interesting thing. But if there's an even number amount of inputs, then it'll give you a 1 as an output. It's kind of like the inverse of XOR. It's also a very, very important gate for cybersecurity. Okay, I'm not going to go into too deep into digital logic because you can go down the rabbit hole of digital logic and go into things like Boolean equation solving, K-maps, doing things like large truth tables. I'll tell you that the digital logic course in the EC department makes you do things like 5x5 truth tables. If you do 2 to the power of 5, it's like 32 different outputs, and the K-maps are insane. It gets complicated. But in general, what we talked about so far gives you a basic understanding of how to make key components in computers. In every computing unit, there's usually an arithmetic logic unit, an ALU, that does all the math in the computer. That's built out of the gates we just talked about. There's also the CPU, or the central processing unit, which is also built out of the gates we just talked about. Or the memory bank, right? Registers that can store things, which is built out of the circuits we talked about, right? There's also things like sequential circuits, which can store memory. You know, storing memory is just like kind of like a variable in programming, except like inside of physical hardware. You can go down the rabbit hole, it's endless, but in this case, we're going to stop here and do some multi-sim challenges first. Before I do this, we didn't actually do this in the last cyber and circuit analysis workshop I did last semester, so I'm excited to do it now. But this is why I went ahead and gave you guys a guide of softwares that you can download, because we're going to check out some multi-sim stuff right now. So if you have a computer, or if you're going to be working on this, you can go ahead and bring that up right now. And we'll be using a little bit of, we're going to be using Multisim Live, but if you check out the documents that we've previously looked at, so again, if I go to this document right here, this shows a list of digital logic tools that I really recommend for introductory members to play with, just because I think it's a versatile guide, and also it has some pretty good tools. So for those of you who don't know what this is, or don't know where this location is, this is on the Discord. And also, if you're looking at this on YouTube, is in the description of this video. So here I recommend 5 different softwares that you can download, some free, some paid, in order to learn digital logic at a very deep level. The first one is Multisim Live, which is used in a lot of courses to teach digital logic. The second one is this Digital Logic Sim. Actually, I like this a lot because of how simplistic and minimalistic it is. It's not a SPICE program, but it does get pretty dang close to just like block by block getting things to work. It's also free, or you can donate to this guy who made it. But, you know, in general, he has a lot of YouTube videos that teach you how to use this material, and it gets to a really complex level of building like computers as well. So if you want to go down this rabbit hole, go ahead and download this one. I really recommend it. Tinkercad is another one. Again, Tinkercad is free software. It also has 3D modeling and programming, but it exists for a long period of time, and you build circuits on breadboards. So this is kind of like a 2D simulator of breadboards. All these 3 are free, but if you go down to these ones, these are paid. This first one is Crum Circuit Simulator. It's about $8. It was recommended to me by a friend from the internet, and pretty much it's a really nice rendered model of circuit simulation. And it's pretty brand new, but it's getting updates every day. But if you would like to work with circuits, it even has like Arduino programming and TFT screens. So it's pretty awesome. And it's like all RTX rendered. It's a pretty good deal for $8, and you can learn a lot from it. So I suggest it. It's kind of like building a circuit in real life, except you can do it online. And the last one is Turing Complete. Turing Complete is a digital logic game. It's about $20, but it goes through all the steps of building a computer from the very ground level and using, digital logic and logic gates. So I really recommend this game as well. The story is you can solve problems by impressing an alien superior by constructing a fully functional computer. So now that we've gone over some of this stuff, hopefully you guys have all created a Multisim account. We're gonna just test stuff out and just play with it a little bit. Oh yes, if you have NI Multisim, which is the alternative, you can use that as well. Let me explain the differences. So for CPP students, you can get Multisim for free, NI Multisim, which is the full version of it, from the school's engineering software websites. If you're a high school student, unfortunately, I'm not sure if your school supports that or not, which is why we're using Multisim Live, but the online version is free. It does have a little bit less of a, it has a lesser library, so you don't have all the chips, but it still has enough functionality to do what we're gonna do today. So we're just gonna play with a little bit of circuitry real quick, right? So on Multisim Live, well, I'm gonna create a new file or a new circuit. I'm gonna call it, it's 4x02 now, Circuit Analysis Workshop, and I'm gonna save this. Now, Multisim Live, the only downside to this is all your circuits are public, so it doesn't really matter because I don't have any friends, but that's like the only way they're gonna see it. So Multisim Live is pretty cool. It's like a SPICE software. Now SPICE stands for, I have the thing here. When you're working with SPICE software, it's called Simulation Program with Integrated Circuit Emphasis. And all that means is a fancy word for I can make circuits work. So in this case, we're gonna look at this and we're gonna build a simple LED circuit first to just demonstrate what's going on. So in real life, you work with breadboards and you work with jumper wires and you work with all these kind of like handheld components, but we need a way to reference them in a simulation online. So instead of like wires and physical objects, you use symbols instead. We're gonna go ahead and place a DC voltage, which kind of looks like this. And by the way, this symbol is a battery. In real life, DC voltage sources don't actually exist, so we represent them as a battery to get as close as possible. When you're using when you're using a voltage source inside of a lab, that's not actually ideal. There's still some noise like in inductors and capacitors and a bunch of like different equipment inside that box that gives you that voltage, but it's not perfect voltage. If you zoom in enough, you'll see noise. So in this case, I'm going to simulate a circuit using a 5-volt power source, a passive source, which is a resistor, or all those are passive, but I'm going to use a resistor. I'm going to rename this to 330 volts, 330 ohms. It's getting late in the day. And I'm going to grab a LED. So this is like one of the most basic circuits you can have. Okay? Then I'm going to click on the end of this source and bring it over here to connect it, like that. And I'm going to connect it again, like that. And then like that. Okay. Now I need a resistor for this circuit, right? Just because if I don't have this, the resistor is what's preventing current from flowing through endlessly through the LED. LED doesn't really have any resistance, so if I don't have this, it'll blow the LED up, right? So the resistor limits the amount of current flowing through the circuit. So I can go ahead and start simulating this, right? Or am I missing something? Ground? I'm missing a ground, right? If I don't have a ground, it's not going to be able to know what it's simulating or what its reference point is. So in order for me to make sure that the circuit works correctly, I'm going to put a ground right here. Now usually in circuits, grounds go on like the lowest part of the circuit, but you can put them anywhere you want and it'll work the same. So now let's go ahead and start this simulation. And you can see that, it runs as expected. The LED turns on. There's nothing fun or nothing new to see here. It works as expected. So let's go ahead and stop this and put something more interesting, right? Now, in real life, you would want to see something happen, and this is something we're going to do next week too. So we're going to add a switch, right? This allows the user to do some fun stuff with switches. Now, in Multisim or in real life too, there's two types of switches you can use. The first type is called an SPST. This stands for a single pole, single throw switch, which is a fancy word for there's one input and one output. And this just connects 2 points together. So what I'm going to do is I'm going to go ahead and extend this over here and give this some room for a switch to exist. Like this. I'm going to delete this wire and put the switch right in between it. Like this. So what happens now when I run the circuit simulation is that the LED isn't actually turned on because this switch prevents current from completing the circuit. Remember how I said, if you have rubber-soled shoes on, you're not connected to ground, therefore you might not die if you touch a live wire. That's really bad advice. Do not try that. But you're going to be safe from electrocuting yourself because you're not touching the ground. This switch is kind of like that. It prevents the 5-volt signal from going to the LED, which means the LED is not turned on. But as soon as I complete the circuit by pressing the switch here, ta-da, the LED turns on. And the circuit works. It's really cool. Yeah. So if I wanted to go ahead and measure some properties of the circuit, in Multisim you can do some cool stuff like that too. So let me go ahead and stop this simulation here. If you go to this first bar or top element in this toolbar here, you'll open up some analysis and annotation tools. You can measure the voltage, you can measure the current. You can measure the voltage and current, or measure the voltage potential throughout the circuit. I'm going to measure the voltage and current about right here. And I'm going to put some voltage indicator right here before as well. And then I'm going to put voltage reference above, right here. Okay, actually, I'm going to remove this. When I run the circuit, it'll show me some voltage values, right? And we can see some interesting stuff happens. This blue voltage probe tells us at this point in the circuit, we have 5 volts. And at the point after the resistor, it'll tell me I have about 721 millivolts, which is 0.7 volts. This happens because, remember, the LED will suck up some voltage. It kind of steals the voltage from your circuit, right? There's a 0.7 voltage drop across the LED, which is why it's not 0. Now, we'll see that the current is about 13 milliamps, right? Now, the current, in this case, it's very, very low. If the current's in the milliamps, generally we call that very low current. LEDs can absorb up to 20 milliamps of current, depending on which one you use. Those LEDs that you see that you put under desks and under cars to make it look fancy, those are like addressable LEDs. Those draw 20 milliamps per cell. So in this case, this circuit is actually known as a series circuit. And the interesting property about series circuits is that the current at each point in the series circuit is the same. And you can that's also a property of KVL and KCL, but that's more technical that you don't need to know. But the interesting property about the series circuit is that the current is the same at all points. That means if you put more current probes along each side, like I'm doing right now, nope, it didn't want to exist. And I run it. You'll see that all of the current probes, where it says A, are the same, right? But hold on, 3 of those say it's negative current, while the other one says it's positive. Why is that?
The direction of it? Like there's little arrows.
Yes. So remember that anything in electricity is polarized, which means there's directionability to it. So, like in physics, if you're running in one direction, you may have positive velocity, but if you're running in the other direction, it's negative velocity. Same with current. If you're going in one direction, it's positive current, but you're going to the other direction, it's the same current, but just backward, but just negative, right? So you can see that these arrows state that the current going counterclockwise through this loop is negative, while the current going clockwise is positive. Bidirectional. It's very cool. So in this case, what kind of convention is this using? And by the way, the word convention is kind of like a standard for doing things in electricity. What's the convention here? Clockwise is positive. That's good. Clockwise current is positive. And counterclockwise current is negative. Now, there's an interesting story behind this, right? When we say clockwise current is positive, we're saying that the current from the positive end of the battery going to the negative end of the battery is positive, right? Now, that's not what actually happens in real life. Scientists in like the 17th, 18th century or 18th, 19th century, when they first discovered electricity, they were like, oh, ooh, cool. Electrons move from the positive end to the negative end. We'll call that positive current. But then more recently in the 19th and 20th century, they were like, oh wait, we were wrong. Electrons actually move from the negative end to the positive end. But since people were doing this convention of positive, negative, positive current so long, they just kept that. So now we have two different types of conventions, right? One is kind of like fake because it's easier for us to understand, where current going from the positive end of a battery to the negative end of a battery is positive, and otherwise is negative. But in reality, current actually goes, or electrons actually go this way, counterclockwise. So just, keep that in mind, but almost everyone uses positive to minus is positive, right? Or clockwise is positive. That's the standard. Okay, I'm tired of seeing this circuit.
Wait, if your battery orientation is opposite, would it be opposite?
Yes, let's try that right now. So Mancha just asked, if our battery was flipped, what happens? So I'm going to go ahead and take this out of our circuit real quick, and I'm going to plop it back in, but backwards. So I'm going to take this. Oops, that wasn't the rotate key. If I take this voltage source, and I flip it 180 degrees, now you can identify the polarity of the battery by its symbol. The longer line is always positive, right? So if the longer line is on the bottom is positive and the upperwards is negative, right? The shorter one. So I'm going to put it here, and I'm going to put this, I'm going to connect the dots. I know it's a little ugly. Like whenever I do a project, I always want these wires to be like the neatest as possible.
Wait, yeah, isn't that gonna give you an error?
Let's see. So, what are we looking at here in the circuit? Now that I flipped the battery backwards. What happened?
You went straight to ground. It can't go through the LED.
Yeah, Addie's right. It can't go through the LED, and why is that? It's a diode, right? So what mode is the diode in right now? Reverse bias. The battery going in this backwards configuration means that current wants to go counterclockwise now, because when we're analyzing it, we're saying that from positive to negative direction, that's positive current. So current is now moving in the counterclockwise direction, which is what Mancha said, right? Unfortunately for us, this diode, if we have a positive voltage across it in this direction, it's not going to work. It's going to act as a dam. It blocks all current from passing, right? Which is why we see like very minimal amounts of current in the circuit now. It's a little weird, but picoamps is like 10 to the power of negative 12, right? So there's like barely any current going through. Now, remember what I said about breakdown, right? If I have too much voltage going the other direction, it'll let current through. But in this case, diodes are not ideal devices, which means that very small amount of current can still go through. This is called leakage current. And this current, actually, there's two types of there's leakage current and there's parasitic power when you're talking about devices, right? And parasitic power is kind of like when your device is turned off, but it still uses power. So like if your computer is shut down, it still drains power somehow because of some small leakage current that gets past like the off button. But, in general, that's what happens. You only prevent stuff from drawing power if you just literally remove the battery from the device. But even then, the battery still loses charge over time. So you gotta be careful about that.
Chris,
Yeah.
so if you have something plugged in, like your computer, but it's turned off, can it still use power?
Yes.
So if you want to actually turn something off, you actually have to plug it out?
Well, you just have to stop giving it a power source, really. Right? Because there's no free energy in the world. So you always gotta get it from somewhere. But yeah, if you keep plugging your computer, it'll still use power, even when it's turned off. You can have background apps. If it's like shut down, they'll like internally it'll still do something, right? So yeah, it's not perfect. World's not perfect. You have to deal with it. Yeah.
What if the battery is like completely like drained?
Well, the computer doesn't have power, so it's not gonna use power from a drained battery.
I'm talking about the battery. Like what if the battery is like completely drained to 0 volts?
Okay, then nothing's gonna happen.
Can you revive a battery?
Yeah, it depends on the battery. Okay, now we're moving into power systems. We'll talk about that too with you afterwards. Yes, it's possible to revive a dead battery. No, it's not that safe. Generally, you don't want to do that, but there is a way. Batteries are quite abundant though, so just get a new one. It's not worth saving it.
Yeah, and like there are like rechargeable batteries out there.
Yeah. Okay, I'm getting tired of the circuit. Let's move on to digital logic, right? So in this case, let me go ahead and take, in digital logic, what usually happens, and I'm not too familiar with using this, use a VCC. In this case, I don't know if there's a VCC in here. Well, there's a digital constant. I guess I'll use that. Okay. Remember how when we're working with digital logic, now we just ignore the fact that we have 5 volts, or we ignore voltage, current, and resistance, and we just deal with ones and zeros. So in this case, we have digital signals, and I can put 2 digital constants here. Now, I'll use that as my inputs, right? First, we'll start with an AND gate. Here we have an AND gate, and you can see that, there's a lot of different AND gates. It goes up to 8 inputs. But AND gates, the behavior is what? Yeah, so the output will only be 1 if the inputs are both 1. Monch has to bring me back an iced tea and an ice cream cone for me to be happy, right? So in this case, let's go ahead and we have digital constant as the input. That basically just means we have a 5 volts at the input. We're going to give an output, but we're going to feed the output into a LED. Oh, nope, that's not an LED. LED, take 2. No, I keep pressing R for rotate, but that's not the hotkey for Multisim Live. Third try. Okay, it's Shift R. These hotkeys change per program. It's insane, man. Okay, so we're gonna put this here, and we're gonna connect this to ground, so that this thing can run. All right. Toggle. I'm going to change it to 0 first. So if I press play, we can see that the AND gate isn't powering the LED. But if I change these both to 1, then you can see that the output is powered, right? So again, with the McDonald's example, I think I just really want McDonald's right now. If this is the iced tea and I flick it on, then Monch has to give me an iced tea, but I still want the ice cream in order for me to be happy. So Monch has to give me the ice cream, and then it turns on. That's how an AND gate works. You can put combinations of gates together to make more complex logic, but right now we're just going to test AND gates. We're going to test gates individually to see how the software works. So we're going to delete the AND gates and go ahead and put an OR gate. 2 input OR. Let's put this right here, right? And we're going to connect this to the LED. Toggle this off. Now, who can explain how an OR gate works?
Only one of them has to be turned on for the light to turn on.
Yep, exactly. Only one toggle has to be turned on for the LED to be turned on. So it doesn't matter if it's the top or the bottom or both of them, right? The output will still turn on, which means we have a 1, right? Great. So now we've gone through these gates. Let's move on to more complex ones. And I'm going to go straight to XOR because I think this was fun. 2 input XOR. Does anyone remember the purpose of an XOR gate?
It'll be satisfied so long as one of them will work.
Yes, and we call it what?
That one's in XOR.
Right. So it's an odd parity checker, right? So the property is if the inputs are odd, if the number of 1 inputs are odd, then the entire thing will be 1. So it doesn't matter how many inputs we have, and I'll show you in a bit. But if we have an odd number of inputs, it'll turn on, right? But if we have both of them on, that's even number of 1s, so it turns off. We can showcase this with another switch, right? If we duplicate this and put it on the bottom, and if I don't have a 2 input XOR gate, but I have a 3 input XOR gate, okay, let's see what we get here. So this goes into 1, this goes into 2. Whoa, this goes into 2 and this goes into 3. Okay. Okay, so if I switch all these off, right, you'll notice that the LED only turns on when there are an odd number of high inputs, right, or an odd number of 1s at the input. So if I have 1 here, that's an odd number of 1s, right? But if I flick the second switch, that's an even number of 1s, so then it turns off, right? And it doesn't matter how many input inputs there are, as long as it's an odd number of 1 inputs, the output will turn on, right? Okay, yes?
What's like the maximum pins you can have on one of these? Because I only see 8 up to here.
Yeah.
If you want 16 and you put 2 of these connected to an AND, would that give you, out of 16, you need an odd number?
Not an and, you have to XOR them together.
How do you change the amount of inputs?
So to change the amount of inputs, you just click on this icon right here, and then you click on, it's a folder. So this will be the folder of things, and you can just click on 8 inputs. So in real life, this 8 input XOR gate, I don't think any chip has this functionality. It only goes with 4 if you're lucky. So if you want like a 3 input OR gate, XOR gate, or a 4 input XOR gate in real life, what you have to do is you have to combine them. So what I have to do in this case is if I wanted to make this in real life and I did not have a 3 input XOR gate, what I have to do is to use 2 XOR gates. So let me go ahead and do that. 2 input XOR gates. I'm just going to duplicate this, and I'm going to connect them like this. Connect 1 input here. Connect the second input here, and then third input over here. And this goes into my output. I know this is a really weird and wacky. So this would be a 3 input XOR gate, right? Works the same way. You can see how the signals are actually turning on and off, which I think is awesome. But you know, again, you'll only have an output of 1 if your number of high inputs are low. I mean, number of high inputs are odd. Right? Does it make sense? Cool.
If I wanted to make 16, I would need 15 of these?
Yeah.
Oh,
Yeah.
that's annoying.
Yeah. I don't know what you would want a 16 input XOR gate for, but you know. The more the merrier. All right. So now we'll spend the last 20 minutes doing some activities that I have situated on this PowerPoint here. There are 2 different activities in which I will go ahead and send this PowerPoint. Actually, you can see this PowerPoint from the previous semester, but I'll leave one of them up depending on which one you guys want to do. So I have 2 challenges proposed to you. The first one is going to be creating a multi-sim circuit for the scenario with a bunch of voltage regulators in a daisy chain. And the other one is digital logic. I think I'll have you guys do digital logic. You guys can do challenge 2. You guys don't have a choice. So this one is to create a multi-sim circuit for the scenario in which the CPV Hyperloop pod has a set of 2 switches that are able to instruct the pod on what actions to take. The output of the system includes a red LED for toggling brakes, a green LED for toggling motors, a blue LED for toggling an onboard camera, and the switches form a 2-bit input that follows these states. So state 00 will test brakes with the following outputs for LEDs. State 01 will test the motors and the brakes with the following outputs as those LEDs, red 1, green 1, blue 0. State 10 will test the camera, in which it'll have the output as red 0, green 0, blue 1. And state 1 will activate everything, which is red 1, green 1, blue 1, right? You're going to create a circuit that can accept a 2-bit input and display the correct output, I'm covering this thing with my face, for each input state. There are 2 inputs and 3 outputs for the system. Okay. Now, when you get some sort of big, large, fancy word problem like this, the simplest way to go about doing this is to make a table first, a truth table, as one would call it, right? A truth table, again, as we've seen in the previous slides, consists of an area for inputs and an area for outputs, right? And then based on that truth table, you can find out what series of gates to use to be able to power the outputs, because each of the outputs is a separate circuit, if that makes sense, right? So we're going to spend the last 20 minutes doing this activity right now. So each of you guys can work with each other, or we can go over this as a group later on. But we're going to spend the rest of the workshop doing this until 8. So yeah, go for it. Yeah. Huh? You're just going to go to sources and go all groups. So usually what the gates are is if you click on the components, sorry, the name of the input. You're gonna search for before you just dragging. So you're gonna type in 74LS.
So we know that blue. Blue.
Okay, and then those are all the gates you're gonna use. So an AND gate is 0 gates. It's a key.
But blue one and two.
Zero from
If you
that.
check the
So-
table
This one is more
above,
like
you
the,
can see that blue
the numbers, okay.
will
So 0 gate would be
correlate
AND.
to
32 would be or I'm gonna
Chris,
write
can you
it
roll that? Okay, there you go. Yeah, so the first digit on the side, the first input. The second digit on the
Yeah.
So you see the first input correlates to like whether or not the blue.
You guys can go ahead and use markers if you
So
want.
we're gonna basically run the blue light on the side first.
If you're using anti-multisim to search for gates, you have to
Let's get the
do.
easy one out of the way. Deal with each light one by one.
Which ones? Yeah, actually, even very.
So we're just gonna connect the first input directly to the blue light. Because the blue light's on, first input's gonna be on. Blue light's off, first input's gonna be off. So connect to the
Josh, what's O2?
O2 is the O4 is the O2 is the OR gate. No.
No, 32 is
O
O.
no. O2 is the NOR gate.
Or 2. Okay, sorry, yeah.
No, 32 is the NAND gate.
32 is OR.
No, O2 is the NOR gate.
Yeah.
wait,
Yeah.
wait, what are we doing here?
That's for
If you're using anti-multisim, these are the
Okay,
gates.
and I'm
What's XOR? Is it 80, 86?
yeah 86.
that's gonna be a blue. Blue border.
What's inverter? Is it 04?
Huh?
Is inverter 04?
O4 yeah. Then it's part of the truth table. You know, you have your first input, your second input, your first, your 4 states, right?
So red.
0, 0.
Red is 0, 1, 0, 1. So we're gonna connect red to
Have
the second
3 LEDs.
input.
Alright,
So
Maria,
Red, connect red to the second input.
Maria, this is going to be your
Oh,
table
Oh,
of.
okay, thank you.
Yeah. So state zero in first state, red is 1, green is 0, blue is 0.
No, keep the
Red is
lights
1.
down.
Keep lights down.
There's battery on my device.
Right. Second one is 0.
No one.
It's gonna be the.
All right, for the recording, I'm gonna pause it and then replay it when it gets back to 8.
No. Just give me like just like 3 minutes.
All right.
I'm
Well.
building the circuit. I got it.
Okay. Well, I'm gonna go ahead and set this up for this solution here. Display off. So that Zoom can also see what the solution is. By the way, for those of you who don't know what is going on the right-hand side, these are the names for DIP, dual inline packages, which are the most common logic gates that are used for like real-life building. So next week you'll actually get a set of these gates to play with, and you'll get to play with digital logic in real life. Okay, now let's explain the solution because I think everyone's confused. Okay, does everyone know how this truth table came out to be? Right, that's directly from the word prompt, so it's just processing it. So I'm gonna see where my, okay.
Wait, can I see the prompt again? Like the prompt.
Okay, give me a second.
Oh, okay.
It's technically written up there though, on the truth table.
Oh, okay. The truth table.
Yeah, you know what? Okay, so just trust me that the truth table goes, the problem goes to this truth table, right? So we have 2 inputs, right? We have A or we have B. And then we have 3 outputs, right? We have the red LED, the green LED, or B LED. And we're just going to put this L1, L2, L3 because there's going to be 2 Bs. That's smart. Okay. Now because there's 2 inputs, how many combinations are there? 4. Pretty easy, right? 4 combinations are going to be 0, 0, 1, 1, like this. Okay? So L1 has the output combination of 1, 1, 0, 1. L2 has 0, 1, 0, 1. And then we're going to do 0, 0, 1, 1. So there is a mathematical and logical way to solve this, but I'm not going to teach that to you yet because it takes some time, right? So we're just going to use our brains and just treat this as a logic puzzle. Like, how do we make it so that this combination gets all three outputs? Now, the thing you want to do when solving this is to treat each output as individual circuits because each of the outputs do not have any combination with each other. They do not affect each other, right? They're independent. So what we're going to have to do is we're going to take these individually and solve them individually and then combine them all at the end. Now, L1 is kind of annoying to solve, so we're going to leave that one out for later. We're going to start with L2. Okay. Now, we're going to simplify this table so that it looks better for L2, right? I don't know if Zoom can see this. Zoom cannot see this, but okay, hopefully we can see it. So L2 is going to look like this. We have two inputs for L2, right? 0, 1, 0, 0, 1, 1. And L2 is going to be 0, 1, 0, 1. We're going to treat each of them independently, right? Because it's a lot easier to analyze this than this. You get confused a lot when you're looking at this mess. For L2, what kind of pattern can you see between the inputs and the outputs for L2?
B correspond with L2.
B directly corresponds to L2, right? Basically, if I hide the A column, you'll see that when B is 0, L2 is 0. When B is 1, L2 is 1. Correct? Right. So we call that a follower, when the output directly follows the input. Right? So we know that B, whatever B is, L2 is going to be, right? But unfortunately, we have another input to deal with. So now we can cover up the B column, do the best I can. Can you see any pattern between A and L2? So when L2 is 1, it doesn't matter what A is, right? So that's kind of the logic we're going at here. The only time L2 is going to be high or L2 is going to be on is in these two situations, right? And we can see that it doesn't matter what A is, but as long as B is 1, L2 is 1. So in that case, we can just go ahead and say B goes directly to, I'm going to use this as a probe, L2. So no logic gates needed at all. Right? Okay. Does that make sense, everyone? Right? We can go ahead and go through all of the combinations to make sure this works, right? So if I go ahead and take like another marker, like green here. This marker sucks. Yeah. Okay. So to make sure this circuit works, we go through all the combinations in order to check that the outputs are expected. The first combination is 0 and 0, right? So if A is 0 and B is 0, we expect to see an output of 0. Do we get that? Yeah, right? Okay, now we do 0 and 1. If we have 0 on A, this marker also sucks. I'm running out of markers. Okay, I'll do green then. Okay, if I have 0 on A and 1 on B, my output is expected to be 1. What's my actual output? It's also 1, right? So that's good. So check these two. Now let's do the third one. 1 and 0, so A is 1, B is 0, and what do we get at the output?
0.
0, right? And it matches. Good. And the last one, if you have 1 on here and 1 on here, what's our output?
1,
1, right, yeah, exactly. So, this circuit is correct for L2. It's just a B follower. Alright? So you didn't even know like K-maps or Boolean algebra or all the complex stuff.
That's the first thing I think about.
I try to make this one as simple as possible. So, let's do L3 now. Right? L3, truth table, if we extract it from the top one, looks like this. 0, 0, 0, 1, 1, 0, 1, 1. And L3 looks like 0, 0, 1, 1. So what we do is we focus on what combinations make up an output of 1. And it's these two, right? So, what pattern can you see between the inputs and the output? A is always 1. Yes, A is always 1. That's a good point. Anything else? No, B doesn't. It looks like doesn't matter what B is. It's always going to be 1, right? So if this is true, that means this is going to be an A follower, right? Because it doesn't matter what B is. You know, it's always going to be 0 or 1. L3 is always going to be 1, which means our circuit now looks like this. With this being L3, right? Still no logic gates in sight. Okay. So, does that make sense, guys? Okay. So now we have L2 and L3 solved, and we're going to tackle the B status L1. Because L1 is not that simple. So in this case, we have our truth table here with A, B, and L1. 0, 0, 0, 1, 1, 0, 1, 1. Okay, and we have 1, 1, 0, 1. Guys see any patterns?
Yeah.
Yes?
It has to be not either both of them on. Is okay, so it's exclusive OR, and it has to be the A that has to be on for it to shut off the output.
Okay. So you're saying it has to be exclusive OR?
Yeah, I mean like both of them either have to be on. So like both of them for for L2 to not give out an output, it has to be first of all neither both is like with only one or the other on, and it has to be the A on.
Let's hold that thought. Do you have a suggestion?
Yes, I would use an OR gate
And OR?
and B directly to the LED.
Okay. So you're saying basically if B is on, then the LED is on, right?
Yeah.
Okay, that's a good idea. But watch out, because if B is 0, it's also on. That's the first option. Right? So that's a good idea, but let's hear from other suggestions first.
That's why I would use the OR.
Oh, and OR. Oh, NOR. Okay, I'm going to put this up. Okay. Yes?
I'm just noticing a pattern since L1 gives 1 when both A and B are the same value.
Mm-hmm.
A and B both have 0, 0, and the last one, 1, 1 equals 1.
Mm-hmm.
And then going into the middle, does A in that case, since 0 and 1 make the L1 value 1 in the second column, does that mean that the B value is given more weight than the A1?
Nope. Nope. But you are onto something with the XOR. So what he said was basically, you know, this is the XOR pattern, right? You know, 1, 0, 0, 1. Actually, this is, XNOR, right?
Yeah.
So this is the XNOR pattern, where it's an even parity checker. So the XNOR, if we use XNOR in A and B, it will give us this, which is almost the correct answer, but remember we have like this little pesky one that still needs to be added. Yes, Masha?
So can we have an XOR
Mhm.
and I'll handle the topmost case and the bottommost case and connect that with an OR that checks if A is on? So the XOR handles the case and I'll turn it on for those two cases.
That is, you're on the right track. You're very close. Not exactly, because you'll run into issues. Masha's very close. So we have an XNOR case, but then we have to take care of this one, right?
Yeah. So if you put an OR gate at the back of it and connect A directly to the OR gate and then connect the XOR to the OR gate, will that turn it on?
That will eliminate. I do like that. So that is okay. That's one potential solution. You can try it on Multisim to see what happens. Any other suggestions? Eddie? Oh, yeah.
Can I do it that way?
Yeah, you draw. Come on.
Use the meaning blue one.
No.
Hey, Chris.
Yes.
I have this.
Oh, thank you.
Another blue one?
Oh, thank you.
Masha's the closest so far.
Okay.
With the OR.
How is it?
X.
No.
X door.
I don't remember.
I don't remember either. Huh?
It's the or with an extra lamp at the back and then there's not.
Oh, okay.
Yeah.
It's
Like this, right?
Yeah. And then a ball in the front.
Oh.
Where do I connect ground?
Oh.
Hmm. So this is also the circuit that Mancha suggested, which is the XNOR plus the OR gate. Let's see if this works. So the best part about all of this engineering is because we can check our work. So let's see. If we have 0, 0, because we have to get all 4 cases right? 0, 0. What is our expected output?
1.
Okay, so our expected output is 1 because if we have 0, 0 here, then the output of this XNOR gate is 1, and this OR gate, 1 and 0 become 1, right? First case is correct. Okay. Next case, erase these all the time, is 0 and 1. Okay? If we have 0 and 1, what's the output of the XNOR gate? 0, right? And then the input of the OR gate is still 1, so what's the output? 1? Good. Okay. Okay. Now we have 1 and 0. What's the output of the XNOR? 0. And the output of the OR? 0. Oh, looks good. And then finally we have 1, 1. What's the output of XNOR? 1. And what's the output of OR?
1.
It works. Yeah. I think that's a simplified solution. So
They work?
yeah, it works.
Yay.
So let me go ahead and just quickly explain. If you wanted to hard code it, you would have to find a specific situation for where this is 1, right? But it would simplify down to this solution. So the solution that, if you were just to hard code it, was to go ahead and look at the fact that A and B were 0 and 1, and just say this. So it would be XNOR plus, not AB, right? And XNOR is the funny looking symbol, right? With A not A XNOR B plus not AB, right? And then you can say, okay, that just simplifies down to this sort of circuit right here. So even if you didn't know any Boolean algebra, which is what this is, you would still be able to logic your way out of the situation. So this would be your complete solution, right? Any questions?
You know, maybe here, but I think the wiring is totally wrong. So it's not working.
Oh.
The logic works, but the wires don't.
Okay.
I'm like, this looks so bad.
All right. All right. Any more questions about anything we talked over today?
Oh, they only ground? Oh, no wonder they're all.
Nope. Oh yeah, take a picture. So if nothing, then thank you so much for coming today. It's been great having you all. Make sure you sign up for Circuit Construction Workshop 4 minutes tonight. You don't want to miss out. Yep. Thank you, everyone. I'll see you all next week. Bye bye.
Bye bye.